Hello, welcome. So in this series, I've been building an FPGA stack machine CPU from scratch. And in the previous episode, we made a handshake module, which looks like this. Oh, and I still have the text in here. Whoops. Anyway, I'll delete that later. In this episode, I'd like to start using this. So yeah, let's get into it because this might end up being a fairly long episode. I may have cut it out of the previous episode, but I basically wanted to do the jump part of this circuit in the previous episode, and then it ended up taking all episode to do the handshake, and I misspelled hand. Let's just fix that really quick. Okay. So yeah. One of the weird things about the layout mode for the digital circuits is that the clock doesn't have the thing on it, and that kind of bugs me. But I'll try not to look at that. If anybody has Java experience, I bet you that's a small enough fix that it would probably get accepted. The developer of digital is not accepting any large changes, but just fixing that would be really nice. Just saying. Anyway, all right. So we've got the fetch part of this circuit that I'd like to try and get moved over to using the handshake. So let's just try and do that and see how it goes. Okay. So far what I've got is I put an instruction register here after the program memory, and in the FPGA, this becomes just a block RAM, essentially. Or the instruction register here would become like part of the memory or part of the I/O infrastructure. So there'd be like a register in the I/O buffer or whatever. So we can't really put anything between the program memory and the instruction register. So that's going to convolute things in just a moment because we'll have to put some muxes on the output to nullify things. But yeah, so then this enable signal would probably go external to the program memory, maybe? I'm not really sure how that's going to work. But we'll figure that out later. Let's see. In the meantime, I've taken the halt signal here and just instead of it being a wire that runs all the way over here, I just put it into a tunnel. So we've got that on a tunnel and going into this logic here to, if halt is high, then nothing happens in the fetch unit, and basically the whole processor screeches to a halt. We might actually be able to do that differently with the ready signal somehow. We'll reevaluate that in a moment. Yeah, we might be able to just make the halt signal go into ready with an inverter or something. Yeah, we'll see. So I guess the next step would be to pipeline the program counter. And actually, there's going to be a website that I'll use to figure this out, because pipelining is a little tricky and there's some nuances to it. Here we go. I'll have a link to the website that has all of these PDF documents on it. It's by Professor Bruce Jacob, and it's the ENEE 446 Digital Computer Design. Quite some time ago, actually. There's some amazing resources on this. Scrolling down, there's this amazing diagram right here that shows exactly how a pipeline processor should work, including some of the control logic. And it just shows a circle, but it describes how the control logic is supposed to work. So let me look. 7 has the stall logic and 3 has the stomp logic. So the stomp logic is something that we need to pay attention to. Yeah. So it basically talks about what we need to do when a jump happens. And specifically, we need to stomp some, well, I guess we'll get there in just a moment. What I really need right now is the instruction memory, program counter, and the increment, as well as this program counter here. I need to know how all of this is wired up. So I'm just going to put this on the side. Now, program counter is here, but this program counter is actually this one down here. So we need to, what I'm going to call the NPC, the new program counter, or the next program counter, or whatever you want to call it. And that will be up here. Let's see. Why am I doing a multiplexer? Well, I'll need it in a second, but that's not quite what I wanted to do. I just need a copy of this, actually. And then we'll call this NPC, not to be confused with non-player character. We're going to need a lot more room. Anyway, I'm just going to mute the audio here for a second, and I'll be right back. Okay, so we've got a program counter, the next program counter, we've got jump mux, and there'll be potentially a third option up here, but we'll get to that later. And then we've got an incrementer that just increments the next program counter, does it? Yeah, it's the next program counter, not current program counter. So we do this, and then I move the adder that's calculating the jump address. It's down here. We'll need to calculate the jump address from this program counter value instead. Where can we put this? It might make more sense to put it over here somewhere. I think this has outlived its usefulness. I think we've got this all implemented. Yes. Okay. All right. I'm going to do the address, the jump address calculation. Now, one thing that you could do in other processors is do this calculation in the ALU. And at some point, that's probably close to where we'll put it. But for now, I'm going to do it here. It has to be on this side of the pipeline, essentially. So on the left side of this will be the fetch unit, and on the right-hand side of this will be the execute unit, essentially. And that's where this needs to be. So I will be right back. Okay. So as we can see, the jump instructions don't work properly. It gets to the first halt and ends up halting the processor, which is kind of to be expected at this point because we're kind of halfway through this. I just deleted the handshake module for now because, well, we got to wire up everything for it to work, and I wanted to test things now. The other thing I did was just clean up this area here. So then the control signals are on tunnels now. So then we get the display out of the way. So yeah, it's broken because probably what we will find is there's now a branch shadow. Let me just see if we turn off real-time clock. I'm just using a hotkey to cycle the clock here. Let me see. So it's jumping right now. See that? The jump is highlighted, so it's jumping right now. And yet the halt that happens right after the jump ends up executing anyway. That's because we have this instruction register here that's delaying the jump by one cycle. So the way to fix that is we need to squash or stomp on the, or annul or cancel or whatever you want to call it. There's a bunch of different names for it. We basically insert a NOP right after the jump. That way that instruction doesn't execute. So let's do that. Now, you might think that this would work, but it doesn't. And I'll show you in just a second here. see, that's what happens. It goes into an oscillation. And the reason for that is that we're annulling the jump and not the instruction after the jump. So we need to actually delay the signal by 1 clock cycle. In the documentation, I think it's CTL3. It takes the jump instruction and it puts that into the stomp, because what it's doing is it is the stomp signal. Let's go back up to the schematic here. The stomp signal goes from CTL3, it goes up and it goes to the pipeline registers, and it goes to basically a reset on the pipeline registers. Now, the problem with the FPGA is that here is most likely a block RAM. And because it's a block RAM, it has this register built into it, which essentially means that we can't easily insert something between here or have a clear on this register. I mean, maybe the block RAM supports that. I could look into it. But it turns out it works just as well to put a mux after this register and just stomp it that way. So that's what I'm going to do. I can look into if there's other ways of doing this. Like if we had another pipeline stage up here that was like a prefetch stage, and then we had the fetch stage with some logic in it. I don't know. But then that makes things take an extra cycle when on jumps and stuff like that. So kind of prefer not to do that. Anyway, so yeah, that's why you have to delay it by 1 clock cycle rather than just take the jump, because this is after the register rather than before it. If it was before it, then we can just annul this when we do the jump at the same time. But like I said, I can't really put anything between the program memory and the instruction register at this point. So after it is, the easiest way to do this is just to use a D flip-flop. And then we've got 1 cycle delay. And where could we put that? It's going to live over here somewhere eventually. Okay, now it's out of the way. Okay, in theory, this should work. Wait a second. 3, 4. The jump happens. We see 5 briefly here, but 5 should be annulled. Huh? Okay, so we've got 4 here. 4 gets annulled. Okay. And then 5 is where we're jumping, just after that 1 instruction. So we've got the jump happened. We jumped to 5. When that happened, we insert a NOP. The NOP covers over the halt instruction that was just after the jump. And actually, it might help if you could see what the program does. I just remembered that I made a note with the program. Okay, so 4 is right here, which is part of the halt NZ. Halt NZ has a jump and halt instruction. So this is the halt instruction right here. We jump right over it and we go to a drop instruction, then continue on our merry way. Let's see if I can put this somewhat out of the way. And I'm just looking at the program counter here to see if it gets hung up. We're on 15 now. So we're here. So we make it past that halt instruction, no problem. We might have some problems once it gets to the jumps around 18. I guess it's on 20 now. So it made it past one of the jumps. 23. And that's success. So I think if it makes it to 28, we've got a working processor. And it did. Awesome. Yeah, so that looks like it's working perfectly. Awesome. Excellent. So the test cases pass. Let's just let the clock go on its own and see if we can make a few loops through and see if the stack pointer ends up being what it's supposed to be. It's returning to 0. That's good. That's really good. Excellent. Yeah, it looks like it's working perfectly. Excellent. So we have a 2-stage pipeline processor now. We've got the fetch unit being pipelined, and then we've got the everything else unit. What would be nice is to actually use this handshake module to handle program memory taking more than one cycle. Currently, it doesn't, but it would be nice to have that as an option. So I think I'm going to do that now. Well, actually, that worked out really well. What I did is I put the jump into the clear input, which I don't know why I didn't realize I could do that before. Anyway, the clear ends up having the same function. It delays the same amount, and then that ends up going into the valid signal. And so on jump, it just clears out the valid data that it had. So that actually works quite well. It's running the entire test program, no problem now. So one thing that we can do is we can put the valid signal low. And when we do that, the whole processor halts, which is really nice. Awesome. And then we can say it's valid again, and it picks up where it left off. Now, I don't know if... yeah, I busted it. Yeah, I don't know how I broke it, but something isn't working right now because it's way off in Never Never Land. So, oh, and it just jumped back into... Oh, it looped around to the beginning again. So I'll have to look into that. There's some bug somewhere where if valid goes low at the wrong time, then it can mess up. Anyway, I'm just going to clean things up a little bit because it's kind of quite a lot of sprawl here going on. So just one moment while I clean this up. Okay. Well, I think that's a wrap. Everything still works. So in this episode, we basically pipelined the fetch unit. We're using our handshake that we built in the last episode, and we're able to halt the processor if memory is invalid, which is good. We got a bit of a bug that we'll have to sort out later with it not working properly. After the valid signal goes low, sometimes that jams up the processor. I'm not sure where the bug is. It might be in the handshake, but it might be somewhere else in the processor. I'm not sure. It might be that we need to do more with the valid signal here, or the enable signal we're not using properly, or something along those lines. I guess we'll find out. But we will tackle that in the next episode. Thank you very much for watching. There is a link in the description to the GitHub repo for this project, and you can use that to find the commit for this episode and play around with it. Highly encourage doing that, especially with pipelining stuff, because it can be pretty tricky. And it might be helpful to be able to go in here and, change things around and see if you can do things better, and see why I did the things that I did and what breaks if it's not done that way. One thing that you might need to do with that is, and I think I mentioned this before in the series, but this path here is going to be specific to my computer. So you'll have to find the program hex in the dig folder when you download the code and fix this. So you'll have to change it in here, and you'll have to change it in the microcode as well. But then once you fix that, it should just work. Also in the description is links in case you're feeling generous. Thank you very much for anybody that does that. It's very much appreciated, but no obligation, of course. I make a little bit of money off of the ads on these videos, not a lot, but if you can help out more, that's awesome. I'm very grateful. I think that's everything. I'll also leave a link to the RISC-16 document that I referenced in this video as well. And this particular program is Digital by H. Niemann. And I keep mentioning that because people always ask. You'll find a link in the description for this program, or you can search for his name and Digital, and you should find it on Google. So thank you very much. I hope you have a great day.